Hi, welcome to this video with a update of the operational performance of the PIM calculator, the PIM simulator, which is embedded in WinRFCalc. With this PIM analyzer or calculator or simulator, you can see what is the passive intermodulation performance in your receive channels when you are designing or making a layout, frequency layout of your base station. Right. Okay. So let's start the PIM analyzer. It's embedded here in the general RF section. So click on that button. And here you see then a submenu popping up, and this is the PIM analyzer here. So let's click on that one. As soon as this main window is opening, you get a request. Do you want to open the frequency settings window? Of course, you answer with yes, because you have to enter this anyway. And what you find here is the window in which you can define how your simulator is going to operate. In this version, we have at present 8 operational channels, channel 0 to 7 on the transmit side. It's here, the TX channels, and there is a total here 8 different frequencies specified. An important feature that we have implemented is that each channel on the transmit side can have a random walk. And the random walk means that the frequency has a random frequency variation between, uh, as you can see here, plus minus kilohertz from FC on the TX side. Now, if you see how this is programmed, they're all the same. It's 1000. So this means that within plus minus 1 megahertz, this frequency has a variation. So it will change between 844 and 846 megahertz. And with this feature, you're actually adding frequency modulation on all these signals here on a random basis, which more or less simulates the modulation of the channels. Because if you do a PIM analysis with fixed frequencies, all the PIM results or the intermodulation results will be on exactly the same frequencies all the time. And that doesn't really make sense in an analysis. So this random walk feature we think is quite important. Now then the next step that you have to define is your analysis band. So where do you want to analyze if intermodulation is falling in that particular frequency range? And most of the time, well actually always, these frequencies and frequency spans are the uplink frequencies to your base stations, actually the frequencies where the mobile terminals are operating. Now, we've defined here a number of channels on various frequencies, and you can, what you see here, define different spans. There's 2 spans possible. You can select 27 or 9 megahertz. So let's define 2 frequency bands here, 1856. So let's change this one. Let's go to this one. So this one is 27. Then we have 3 of 9. This one is 9 as well. Let's switch that channel on. This channel off. Let me see, and let's also switch this one off. So you have 1, 2, 3, 4, 5 active channels. You can see that on the display later on how that is visualized. And after clicking close and confirm, that information is then let's say, put into the lists here on the left-hand side of this window. So these are all your transmit frequencies. The R indicates that this channel has a random frequency variation, as well as this one. If you change, for example, channel number 1, you switch off the random walk, close, then you can see here that frequency is going to be fixed. So let's make them all random. All right, so this is your frequency list on the TX side. Now, if you are suspicious with respect to the generation of passive intermodulation. Next thing what you have to do, of course, as we have done, is define your analysis channels. So these are all your receive channels on your base station. These are the number of frequencies, and there's a number of spans defined as well. We can close this window because it's not required anymore. Non-linear operation, how you do that, let's switch it all off. So now all the non-linear factors, we have second, third, fourth, up to 11th order non-linear factors here. So if you click all on, here you can see this is actually the formula how we are, let's say, imposing non-linearity on the input signals. And by moving this horizontal scroll bar to the left and to the right, you can change the individual factors here. And here you can see the non-linearity curve. So if I switch it off, you can see it's linear. If I switch it on, it's of course it's a kind of a curve, which you can see here what's happening if you change this factor here. Right. So let's close this. So we have a definition of the nonlinear transfer function. We have defined our transmit channels. We have defined our receive channels. Now the next step is detection. Now, if you select this particular frequency here, you can select one single sweep. The sweep one channel button becomes active and green. So if you click on it, the first thing what's happening is that the software makes a complete sweep of all the signals in a frequency range, let's say, and visualize it in the frequency range between 0 and 8.5 gigahertz. So the sampling rate is double, because this is the Nyquist frequency range. And here you see the signals around this 845. These are the 1900 signals here. And these are the three signals in the 3.5 gigahertz band. Now, of course, because this is quite a large frequency range, you see here these two channels here, they look almost on the same frequency. If you can zoom in by selecting a portion of the spectrum, but this is not the way we want to do the analysis. We want to see continuously how that spectrum is looking. So what's happening in the analysis? We make a zoom on the particular part of that spectrum. So this, what you see here, is the center frequency of 867. The span or the width of this channel is 9 megahertz, and the 867 is that frequency here that you, let's just zoom in, 867, 8. So this is 85, so 867 is roughly here. So there is a 9 megahertz zoom here of which is a small portion of this total spectrum between 0 and 8.5 gigahertz. Right, so you can do, of course, a sweep on these individual channels manually. Just select the channel and click the sweep button. Of course, that doesn't make sense. The next step is to see how that is automated. This is the performance of the system without distortion. So if I select this checkbox here, distortion on, then if I do another sweep, first thing is that the main sweep is done here again. So all the signals are represented here on the top graph. And here you can see on the 1856 with a 9 megahertz span that something is happening here. If we do another sweep, then the top graph is changing, and you see here that this interference signal here is moving to this position here. And that's because of all the random frequency variations on all these transmit frequencies, that all these PIM products are going to the left and to the right, so they're changing continuously on their frequency. And This makes it difficult to understand how, how your PIM is really performing in your channel. Now, what is the solution to this? We have designed a detector form. And in this detector form, you can see the list of the active channels. So the gray ones are not active, which is one are inactive. That's channel 1, 5, and 7. Now we can check that here on the channels list. 1, 5, and 7. They are not active. And the green bordered frequency graphs are, let's say, the active channels into which we're going to do the analysis. So what's going to happen? If we have this form available, uh, look at what's happening here. This checkbox here becomes active as soon as you select the detector form. So if you select detectors here, full PIM scan becomes active. And then the program is going to scan through all these frequencies continuously and storing all the data. So let's just start and give you more explanation while the system is running. So we start here. You see it's starting on the top frequency channel 0. It's an 1845 center frequency with a span of 27 megahertz. And if you see these orange boxes appearing on the right hand corner below, then the channel is active, and so it's running through that list here continuously. So what we're doing to see what is now happening with that passive virtual modulation, there is a storage of a total of 10 sweeps. So now we are gathering all the data. You can see here, this is frequency number 3, and we have one sweep done of all those frequencies. As soon as this list goes up again, you see now it's the second sweep. Now, if we've done 10 sweeps, we're able to do a max hold analysis. And what's the max hold analysis? We are actually storing continuously what is the maximum spectrum, how does that look? So all the maximum energies on all those different frequencies, and each sweep we are storing that information. After a number of scans, what becomes clear, how is your channel performing? So what is the influence of nonlinear effects on the spurious frequencies in that channel after a number of sweeps, and also because of the continuously random variation of the input frequencies. And as I said, if frequencies are fixed and don't change, the intermod frequencies are fixed as well. Yeah, and then it doesn't really give you a very good idea what's going on. Now, so there's a continuous variation. We're now in sweep number 4. And as soon as the 10th sweep is done, then the show max hold trace here, this little checkbox here on the detector screen, becomes active, so you can check it. And then you will see a very surprising effect. What's going to happen then is that there will be a second additional line in the graph, which is blue. And that blue line is the line which has is more a memory of each individual frequency point in that graph with the maximum energy ever detected or ever received. Now, what you then see at a certain moment is that that blue graph is actually growing to a kind of a block of frequencies or a list of frequencies where the maximum PIM performance is shown. So let's leave this running just for a while. And you see here that this PIM is doing a lot here in that frequency range here. Of course, there is a little chance of some folding here of the energy if it is higher than the Nyquist frequency. Well, we think it's not really an issue because the analysis that you want to do with, for example, your C-band frequencies here, the frequency offset is more or less close to that range here as well. So we don't think that will give a really big effect. It gives you a fairly good idea what's going on. So this is already the sweep number 8. What can you see here below as well? That the processing time of each sweep is 2.8 seconds. And what is the software doing in that time frame? When we are at channel number 1, the first thing we do is we take a sweep across the complete frequency range up to 8.5 gigahertz. So all these signals are added together in an array. So all these signals are, let's say, a multi-carrier signal. Then we apply the distortion, so that the nonlinear operation is added onto the, let's say, multi-carrier, the multi-tone signal. And then the application, and now look, we click here on the max, and then I will explain you later on what we see. And then after applying the distortion, of course, what we have to do is to get the zoom function. These frequencies we define here actually produce a local oscillator frequency. So with a local oscillator, we are mixing this, a portion of this frequency band down to 0, apply low-pass filtering. This is all DSP stuff, what we're doing. There's a lot of calculation work and filtering work. And of course, the final, let's say, target that we want to accomplish it. Let's say that we want to have a zoomed spectrum, a little portion of the spectrum here, and analyze what's going on. Now here, the PIM detector screen, and something is wrong here, but okay, we will look after that later on. Now, if we click on that screen, just give one click. Now you can see what's happening, for example, in channel number 1. So channel 0. Channel 0, frequency 1845, as defined here in the list. Span is 27 megahertz, so the total width of this graph is 2727 megahertz with 1845 in the middle. The last sweep is green, so if we see a sweep here, then there is a green sweep. And now it may be interesting to observe to this green line here. Let's see if we can zoom in. Let's see, zoom out. Just click on it, and let's zoom in what's going on here. So now you see this green line here. You see now it's becoming blue. Now let's say the next one here. So the max hold was this curve here, roughly. In this last sweep, this signal is actually higher than the saved max hold of the previous sweep. And after the max analysis, you can see that this one will return into blue as well and will be added, there you go, to the overall performance. So let's do the unzoom again. Click, one click on the screen. So what you see here is that there's a lot of frequency variations here around this 1845. And we are just memorizing all the occurrences of PIM's products here in that frequency range. Here's another bunch of signals as well. Look here, this is a high one. So let's see what's happening then on the next sweep. That one becomes blue, and there's another peak then here. Here's one as well. There's one. And you can see that this blue line is slowly growing over that green line here. So the green line, after we've processed the max hold function, the green line is always falling under all these blue lines, because that is the maximum which we have ever observed. Okay, so let's click on this one. Click on that one. Oh, that looks a little bit different here. You see that the function is doing exactly the same here. Now this green line, this spectral line is a little bit higher, and becomes then green as well. Okay, all right. So this is what we would like to show you. this is the performance of the PIM analyzer. And what is the future going to bring us is that this particular calculator will be taken out of the WinRFCalc as a separate program. We will make a new definition of a program called PIM Calc, this WINPIM Calc, will be, let's say, promoted on a new website. And that will be one single calculator with all these nice features, which could be an interesting tool for the telecommunications market to find out what's happening with your interference if you're transporting, let's say, you're transmitting multiple signals in the radio spectrum. It's not only for base stations. We can also use this, for example, in active systems like tunnel repeaters, where you are transporting multiple signals and amplifying multiple signals on broadband amplifiers with, let's say, the risk of causing intermodulation in those frequency bands. Well, thanks for your attention, and hope to see you soon again on the next video. Thank you. Bye-bye.